Hey guys, another video of sequences and series. Today we're going to do alternating series and ratio and root tests. The first test, alternating series test, is a series whose terms are alternating positive and negative. You usually see those when you have -1 to the n plus 1 power or -1 to the n power. Be careful though when you have series that say -1 to the 2n power or -1 to the 2n plus 1 power. 2n and 2n plus 1 are always, this is always even and this is always odd. That means that it's not alternating. Okay? Other cases where it might be alternating and you don't realize it is when you have like sine of n pi over 2, because that makes it go in between 1 and -1, and also when you have cosine of n pi or pi n, that alternates between 1 and -1 as well. So you have to be careful. If you ever see those two things, then know that those two mean that it's an alternating series as well. So you'll see these or those two, and if you see those, then you automatically go to alternating series test. Okay, now in general, knowing that the limit equals 0 tells us not much about convergence of the series. Because remember when we do nth term test, do you remember nth term test from back in the day? And if the limit does not equal 0 for nth term, it automatically diverges. And I said if the limit does equal 0, then it doesn't really do anything, like you have to do another test. Well, in alternating series, if the limit equals 0, and it's alternating and the terms are getting smaller, then it's going to converge. So alternating series test says that a series will converge if they are alternating in sign, are getting smaller in magnitude. They say magnitude is because when it's alternating in sign, it doesn't really matter what the sign is. It's just the size of the term. And the limit equals 0. So if you prove those three things, then you can say that it converges by the alternating series test. Now, if the limit does not equal 0, you do not say that it diverges by the alternating series test. If the limit does not equal 0, then you say that the series diverges by the nth term test. Okay? So it doesn't matter whether it's alternating or not. If the limit does not equal 0, you go automatically and say that it diverges by the nth term test. Okay? All right, let's try an example. So determine whether the following series converge or diverge. -1 to the n plus 1, well, that section of our sequence is the alternating part, so it's alternating sign. 1, it is alternating. 2, what we need to prove is that the next term, n plus 1 over 2 times n plus 1 minus 1, is going to be smaller than the previous term. And that is n plus 1 over 2n plus 1 is going to be smaller than n over 2n minus 1. And that's true. So it's decreasing in magnitude. And 3, we need to prove that the limit as n goes to infinity of the part that's not alternating, 1 over n over 2n minus 1, goes to 0. But what does this limit go to? This limit goes to 1/2. All right, that's not equal to 0. So if it's not equal to 0, we are not going to say it diverges by alternating series test. We are going to say that this diverges by nth term test. Okay? All right, one more example of alternating series test. The part that tells you that it's alternating is this one. The part that tells, or we have to figure out whether it's decreasing in magnitude. So 1 over n plus 1 is going to be smaller than 1 over n. And then we have to say that the limit of the non-alternating part is going to equal 0. And this does. When you go to infinity of 1 over n, it equals 0. So therefore, this will converge by alternating series test. But remember, only by alternating series test can you say that if the limit equals 0, it's definitely going to converge. Okay? Now, there are some cool things with alternating series, and that's called the remainder or the error. Now, the alternating series remainder says that if a series converges by the alternating series test, if the sum is approximated by the nth partial sum, then the error in the approximation is going to be less than the absolute value of the next term in the nth partial sum. Okay? And this is kind of hard to understand. It's better if we do an example. Let's say that we have this series right here, negative 1 to the n minus 1 over n factorial. Now, we can prove that it's convergent by the alternating series test by saying that it is alternating. That's the negative 1 to the n minus 1 part. It is decreasing because 1 over n plus 1 factorial is less than 1 over n factorial. And then we can also say that the limit as n goes to infinity of 1 over n factorial will go to 0. So it does converge by the alternating series test. Okay? Now, this question is saying approximate the sum of the series by using its first 4 terms. So the sum of 4 terms would be, all right, let's plug 1 in initially here. So 1 plugged in here is negative 1 to the 0 power. That's 1 over 1 factorial is 1. We plug 2 in and we get negative 1 over 2 factorial, and then you get plus 1 over 3 factorial, and then minus 1 over 4 factorial. So if I added them all up, you get 1.70833. All right, now explain why your estimate differs from the actual value by less than 1 over 100. Alternating series error says that the error in my approximation is going to be equal to the value of the next truncated term. So the next term in this sequence would be the absolute value of 1 over 5 factorial. Error is always positive, so that's why we're doing absolute value. So the next term would be 1 over 5 factorial. Well, 1 over 5 factorial is 1 over 120. if I can say that my error is 1 over 120, and I want to prove that it's off by less than 1 over 100, well, my error is 1 over 120. That's less than 1 over 100. So that's why you can explain why your estimate differs from the actual value. You can say by alternating series error. Okay? And if you actually wanted to find what your actual sum as you went to infinity would be, you would take the approximation up to 4 terms and add subtract 1 over 120, and you would add 1 over 120, and that would give you your actual value. So let's take that and let's calculate it. So my actual sum, infinite sum, would be in between 1.7 166 and 1.7. Okay? Okay, so next, how many terms are needed to approximate the sum of the series? -1 to the n plus 1 over n to the 4th. So the estimate differs from the actual sum by less than 1 over 1,000. So I want my error to be smaller than 1 over 1,000. So let's just go, let's type in the terms. 1 inside there would be positive 1 over 1 to the 4th, 1 over 2 to the 4th, over 3 to the 4th, okay, so those are the terms of my sum. My sum would be that, the series would be that added together. And if I calculated 1 over 1 to the 4th, that's 1. And 1 over 2 to the 4th is 1 over 16. 1 over 3 to the 4th would be 1 over 81. 1 over 4 to the 4th would be 1 over 256. And 1 over 5 to the 4th would be 625. And then 1 over 6 to the 4th would be 1 over 1296. So I'm going to stop here. So I need 5 terms because this term is going to be my error. And my error is 1 over 1296, which is smaller than the error that was requested, 1 over 1,000. So I know that if I estimate up to 5 terms, I'm off by my actual infinite sum by 1 over 1296 at maximum. And so that's a good enough approximation to satisfy a 1 over 1,000 error. Okay? All right. 2 more tests to learn. And then that's it. So there's ratio test, and ratio test says that if you have a series, if you do the limit of the next term in this series divided by the previous term, if that's less than 1, your series will converge, and if it's greater than 1, your series will diverge. If your limit equals 1, the ratio test doesn't work, so you need to choose another test to do. Okay, you use ratio tests often when you see factorials. So if you see factorials, you should probably use ratio test. All right, let's do some examples. Let's evaluate the limit as n goes to infinity of the next term in the sequence, which is 2 to the n plus 1 over n plus 1 factorial divided by n factorial over, 2 to the n over n factorial. Let's multiply by the reciprocal. 2 to the n plus 1 can be simplified into 2 to the n times 2 to the 1. And we'll flip this. And n plus 1 factorial I can actually simplify to n plus 1 times n factorial to help us simplify. These two cancel. Those two cancel. So this limit is 2 over n plus 1. As you go to infinity, this limit is going to go to 0. And if that limit goes to 0, that's less than 1. Therefore, this series will converge by ratio test. Okay. All right, you try the next two. I'm going to put the answers to them up. So you might want to pause this video and try them on your own first. So I did the other two problems, and both of them diverged by the ratio test because they both had limits greater than 1. This limit actually went to infinity, which is definitely greater than 1, so diverges by ratio test. right, last test of them all, root test. Root test says that it will converge if the limit of the nth root of the sequence is less than 1, and it'll diverge if the limit of the nth root of the sequence is greater than 1. If it equals 1, it's inconclusive. You gotta do another test. All right, this root test is good if you have things to the nth power. So if you have things to the nth power, you can do root test to it. All right, 2 last problems. What you want to do is you want to do the limit as n goes to infinity of the nth root of your sequence. If I take the nth root of e to the 2n over n to the n, that equals e squared over n. And as n goes to infinity, this goes to 0, which is less than 1. Therefore, this series converges by root test. Not 3 zeros, or 3 O's. And the last one. So the nth root of 3n plus 4 over 2n to the nth power, the n to the n cancels out. And this goes to 3/2, which is greater than 1. So this series diverges by root test. Done. Yay, congrats, you've learned all the tests. Now it's a matter of applying all the tests that you learned. See you next video. Bye.